Okay, we're back for lecture 12, I think. First of all, are there any questions? So everybody's okay with it. All right, so let me review quickly what we did last time and then continue on. So last time we were talking about the important classical Erlang delay model, or Erlang C model, or MMS. So this notation, the so-called Kendall notation, this means Markov or memoryless or Poisson input. And this means memoryless or Markov or exponential service times. This means S servers, and then it's assumed that we have infinite queuing capacity. And we had developed the rate up equals rate down equations to derive the state probabilities. And then we wanted to calculate the waiting time distribution function. So to do that, we started by calculating the probability that the customer waits longer than t. And we started with the theorem of total probability, which says that the probability that he waits longer than t is the probability that when he arrives, he finds all servers busy and j customers waiting in the queue in front of him. That is, he finds state s plus j, multiplied by the probability that he waits greater than t if, when he arrives, he finds s plus j. In this equation, the n is the number of customers found by an arriving customer. And we sum this for j greater than or equal to 0. And then we make some substitutions here. First thing is we recognize that the pi's are the same as the p's. And the p's are what you get from solving the rate up equals rate down equations. And the reason for that is pasta. That is, we're assuming that we have Poisson input. And we proved that if we have Poisson input, the arriving customer sees what the outside observer sees. So that allows you then to replace this by the state probabilities that we calculated. And then we have to calculate this conditional probability of waiting longer than t if the number you find in front of you is s plus j. That is, if all s servers are busy and there are j customers waiting in the queue. And this turned out to be given by the following. It's the sum as I runs from 0 to j of s mu t to the I over I factorial e to the minus s mu t. Now, where this comes from is several things. First of all, the strategy was to say, well, when a customer arrives, then if we're assuming that he finds all the servers busy and j in front of him, well, let's say that there's the j customers in front of him. And there's our test customer right there. So he has to wait for the service completion of at least j plus 1 customers before he will enter service. Now, if the queue discipline is FIFO, that means that he has to wait for exactly those j plus 1, that is, these j all to enter service or leave, so that altogether there's a departure process here. And if it's FIFO service, then he's going to wait longer than t if and only if the number that he finds, the number that depart in front of him, if he finds j, is j or less. Now, when these guys depart, during this time, all servers are continuously busy, which means that the times between departures are the minimum of the service times of the guys in service. And by the assumption of exponential service times, every time somebody departs, his place is taken by someone else whose service time starts from the beginning, but all of the others also restart in a sense because of the Markov property of the exponential. So you can see you're using two things very strongly here. One is you're using the fact that we have FIFO service. Okay, so this is FIFO, first in, first out, because this equation, which is from the theorem of total probability, is valid for any order of service. But now we're going to actually calculate this piece right here for FIFO service. The other thing is that we've obviously used the, the fact that the service times are exponentially distributed in a rather strong way. Now, if the service times are exponentially distributed, then the times between these departures are the minima of the service times. And we know that the minimum of an exponential is again exponential. So in fact, since the times between departures are IID, independent, identically distributed exponential variables, that means that the number of departures that occurs in a fixed time must have the Poisson distribution. This is the Poisson probability that in a Poisson process whose rate is S mu t, whose rate is S mu, that within an interval of length t, exactly I Poisson events will occur. So this then is the probability of exactly I departures. When I sum it from I equals 0 to j, I have the probability of j or less departures. And if I've had j or less departures, and the test customer finds j in front of him, then he will weight greater than t. So I plug in the formula for the p's that I got from solving rate up equals rate down. I plug that in. I have a double sum. I rewrite it. The rest of it is just arithmetic. And when you get done with all the arithmetic, this is what I did in class last time, what you get is the following result. The probability of weighting greater than t is equal to the Erlang C value, that's what comes out of the simplification here, times e to the minus 1 minus rho S mu t. And this is equation 4.25 in the textbook. Of course, it presumes that t is non-negative. Rho is the utilization, and mu is the reciprocal of the average service time. All right, this is a really nice, simple formula. And from this, we can get some insights. The first thing is to notice that you can always write that the probability of weighting greater than t is equal to the probability of weighting greater than 0 times the conditional probability of weighting greater than t if you weight greater than 0. This is just from the definition of conditional probability. Now, with that observation, I could see that since these two things are the same, and since the Erlang C represents or is equal to the probability that you have to weight, therefore these things are equal. And if those are equal, that means that these things are equal. So therefore, we know that the probability, the conditional probability that I wait longer than t, given that I have to wait at all, is e to the minus 1 minus rho S mu t. So this says that the conditional distribution of waiting times, given that you have to wait, is exponentially distributed, and its parameter is 1 minus rho S mu. So therefore, I can immediately write that the expected value of the waiting time, given that you have to wait, so this is the conditional average waiting time. This is the waiting time for those customers who have to wait, must be given by the expected value of this exponential variable. So and we know that for an exponential distribution, that the expected value is the reciprocal of this parameter. So this is equal to 1 over 1 minus rho S times mu. And mu, 1 over mu, of course, is tau. So I can bring the tau up there in the numerator and write it like that. So this is a very nice, simple formula. It has some characteristic properties. One of them is that you can see that as the utilization goes to 1, the denominator here goes to 0, and the average waiting time goes to infinity, which, of course, is just what you would expect. Note that if I were to calculate this in terms of average waiting time, if I divide by the average waiting time, then this represents the average waiting time in units. Excuse me, if I divide by the average service time, this formula represents the average waiting time in units of average service time. Now notice that, or it'll turn out to be true, that although this result requires that I have FIFO service, because that's where it came from, this result, even though it came out of that, will turn out to be true for any order of service, and I'm going to prove that shortly. So this is very important. It says it doesn't make any difference what the, whether I have first come, first serve, last come, first serve, service in random order, as long as the state probabilities are in fact given by those, then this formula gives the average waiting time. So the difference between waiting times in the case of FIFO service versus LIFO service, for example, is in the distribution, but not in its average value. Now this stuff is covered in the Bertzekis and Gallagher book in chapter 3. In fact, he covers, now we're in the standard stuff of queuing theory. The theory part has been pretty much handled. And so I suggest that you read chapter 3, at least read the first half of it. That's where we are now. Now, Bertzekis and Gallagher cover the material in a different way than I do, and they don't cover as much. That is, for example, they don't give this result here, and they don't think they give it like this. I'll get to that in a moment. But they cover all of the basic standard results that are in most of the books, and also they give examples of applications in the context of computer networks and data networks. And of course, that's the reason, official reason for giving this course in the computer science department. So I want you to read that to understand the context in which these things are used. Okay, now, if this, let me put the tau back here. If that represents the average, the expected value of the waiting time, let's see, I can go back now and I can calculate the average waiting time for all customers, because the expected value of the waiting time is equal to the probability that you wait greater than 0 times the expected value of the waiting time given that you wait greater than 0. This is a standard formula from probability for expected, for conditional expectations. So that means that in order to get the average waiting time, I simply take this equation here and multiply by the probability of waiting greater than 0, which is the Erlang-C formula. So the average waiting time is equal to the Erlang-C value divided by 1 minus rho s times tau. So this is an important result. Now, it's worth pointing out, and by the way, as before, as I'll show shortly, this is valid for any order of service as long as the state probabilities are given by the rate up equals rate down equation. It's interesting to point out that because this formula shows that the conditional waiting times are exponentially distributed, that means that they have the lack of memory property, which means that if you're in a queue and there's a queue in front of you, but you don't know how long it is, you have no information except that there's a queue in front of you and the queue is being served FIFO, then no matter how long you wait, the distribution of your remaining waiting time is still exponentially distributed with the same parameter as before. So I like to give what I call the restaurant theorem, which says you go to a restaurant and you ask the maitre d' how long you have to wait for service, and he looks at his list and he says something like 15 minutes, let's say. He tells you to wait in the bar. So you wait in the bar, meaning that you're not watching exactly what's going on, so you don't know how many people are in front of you. All you knew is that you had 15 minutes to wait. And then when the 15 minutes are up, you still haven't been called, so you go back to the maitre d' and you say, how much time do I have to wait for service? Continuing, and he looks at his list and he says 15 minutes. And of course, the reason for that is no matter how long you've waited, the waiting time, the future waiting time, is independent of the past waiting time if the service times are exponential and if the order of service is FIFO. Of course, in a restaurant, exponential service times is probably not a good description of how long it takes a person to eat, because by that argument, no matter how long the person has been eating, that is, no matter how much he's already eaten, he's going to eat the same amount before he gets up to leave. So that makes sense for some people, but in general not. Okay, so this means that the distribution function of waiting times for MMS FIFO is given by the following. FW of t is equal to 0 if t is negative. That's obvious, and in my derivation, I presumed that the t was not negative. And it's equal to 1 minus c of s and a e to the minus 1 minus rho s mu t for t not negative. Now, this is interesting somewhat in the following sense. In undergraduate courses in probability, we usually talk about random variables that are discrete or random variables that are continuous. And, of course, they could be mixed. But usually when you have examples of mixed random variables, it looks phony. It's something that the author made up in order to illustrate the fact that this kind of thing could happen. But the examples that are given usually seem rather arbitrary. But this is an example where it wasn't made up. This came out of an analysis. And if you draw this distribution function, you will see, here's what you get. Here is the distribution function of W evaluated at t. There's t. There's 0. When t is negative, the function has value 0. When t is equal to 0, when I jump from this branch to this branch, the distribution function is given by 1 minus the Erlang c value because the exponential term is 1. So therefore, there's a discontinuity, and it jumps up here to 1 minus c of s and a. And then after that, it will look like this. So this is an example. Excuse me, I did it wrong. I was drawing greater than. Should look like this. Here is the 1 minus c of s and a. Let's say the value is there. There's the value 1, and it will look like that, the distribution function. Okay, so what you have here is you have a random variable that's, or a distribution function that's differentiable for t positive and for t negative, but at t equals 0, it's not differentiable because there's a discontinuity. So in fact, this random variable is neither continuous nor discrete. It's a mixture. And if I were to simply differentiate that and call that the density function, I would miss that jump and I would get the wrong answer. Unless, of course, when I take this derivative, I take into account this discontinuity, and then I have a delta function or something like that. So we'll get to that later on in the course maybe, but I just wanted to point out that here's an example of a random variable that is both discrete and continuous. It's mixed, and it's not a phony one that was made up for the purposes of illustration, but in fact, it's one that comes out of the analysis. Now, these formulas, or some of these formulas, like this one, for example, is given in the Bertzekis and Gallagher book. So this is an important one. Let me see if I have an equation number for that. This is equation 4.27. So this is 4.26 in my book and 4.27. Okay, now, before I go on, I want to take things a little bit out of order here, at least in terms of the way it's done in my textbook, and discuss something that is very important, probably should have been done in my book earlier, and is done right up front in the Bertzekis and Gallagher book in exercise in chapter number 3. So I'm going to erase this here. And let's see. Okay, I guess I can erase all of this. And I'm going to consider what's called Little's theorem. So it's called Little's theorem, Little's law, various different names. It was published by someone named Little in 1961. that was the first mathematical proof of something that actually people seemed to be aware of for years prior to that. And in my textbook, it's on page 178, starts on 178, section 5.2. So it's section 5.2, page 178. And the theorem number, the formula number is given as 2.1. And the way the formula is written is L equals lambda W. And often it's referred to by the name L equals lambda W. Now, originally, I think this was derived for or recognized in terms of the same kind of queuing model that we're talking about now, but it turns out to be much more general than that. So L stands for length, I think, or queue length. And lambda stands for the arrival rate, and W stands for the waiting time. Actually, this is expected queue length is equal to the arrival rate times the expected waiting time. So this is very neat because what it does is it connects an average of a discrete random variable and an average of a continuous random variable. So from a practical point of view, it turns out, although we're doing it sort of backwards, that it's often relatively easy to calculate the average queue length. And from that, if I just divide by lambda, I will get the average waiting time. So I can go back and forth between the two, but this is usually easier to calculate because this is discrete and that's continuous. Okay. But it's more general than that. So that's also its beauty. So here's the basic idea. I have this system, and I'll put it in quotes because it's very flexible as to what you call system. And then you have some entities, customers, who arrive and they enter the system at rate lambda. So I'm going to call this a prime here because I want to distinguish between the arrival rate and the entry rate. The arrival rate is the rate at which the customers seek to enter. But in a general case, they don't necessarily enter. And I've used lambda to be the arrival rate, so I want to distinguish between the arrivals and those that actually arrive and enter the system. So I'm going to call lambda prime. So here's my lambda prime. So lambda prime is the rate at which they actually enter the system. So I'm going to call that the entry rate. But in the literature, these symbols are just used now as a name, and this is always written lambda. But I'm putting the prime on there to indicate it's the entry rate. Now, when the customers enter the system, they stay there for an average length of time, which we'll call W, which stands for waiting time. And while they're there, having their lifetimes expire, so to speak, on average, there's L of them present. And the idea is to find the relationship between the average amount of time that a customer spends in the system and the average number of customers who are present having their lives spent. Now, the proof for this, well, Little's original proof was quite difficult and made some assumptions that turns out to be not necessary. And over the years, this has been refined and generalized over and over again. And in fact, there are really many, many papers now that have to do with Little's theorem and its consequences. And if you were to Google Little's theorem, I'm sure you'd find them. And also, Bortzekis and Gallagher give some references, and I give some references, although, of course, the references that anybody gives are cut off at the time at which they give them. So Bortzekis and Gallagher, I guess, was published in the early 90s. I think that was it. In any event, that was maybe 10 years ago, and so there's been 10 years worth of Little's theorem going on since then. Okay, now, one insight from this is that although originally people made assumptions here that were essentially probabilistic or stochastic about the stochastic process involved, it turns out that it's really a deterministic rule, that the stochastic part had nothing to do with it, and that's why this is so, so important and so robust, because this formula is going to hold regardless of whether these arrivals occur according to a Poisson process, and regardless of the service time distribution. It doesn't make any difference. So it works everywhere. The only requirement, essential requirement, is that the L, the W, and the lambda must exist. But as long as they exist, then this is going to hold. Okay, now let me give a quick argument that sort of intuitively, to me anyhow, explains why it's true, and then the rest of it is mathematics, which, as I say, you can look at it if you want, but is not the prime interest from our point of view. So here's the idea. Imagine I look at this over some long period of time t, and I want to imagine that as these customers enter, they bring in with them their lifetimes, and that these lifetimes build up like a reservoir. And so the lifetimes that build up must equal the lifetimes that are used up, and so you equate the two, and you get the answer. Okay, so over some period of time t, the expected number of arrivals that is the expected number that enter the system, would be the entry rate times t, rate times time. And each of those people, customers, whatever, who enters this system then stays there, brings with him an amount of lifetime that he's going to use up. On average, it's W. So therefore, the total amount of lifetime brought into that system in time t is going to be lambda prime t times W. Remember, W is an average value. Okay, now on the other hand, what is the how much life is going to be used up during an interval of length t? And there you could say, well, on average, there are L people in that system, and their lifetimes are expiring in parallel, and they expire at the rate of 1 unit of life per unit of time. So therefore, in time t, if I had one person present, the amount of lifetime that would expire would be t. And if I have 2 people, it would be 2t, and so forth. So if I have L people, it's LT. Now, over the long run, the boundary or initial conditions with the t should be irrelevant, and I can cancel out the t and set these things equal. So the mathematical analysis concerns, well, is it legitimate to cancel out the t? Because the t is going to infinity, and so there's lots of mathematical problems with that. But those mathematical problems can be solved, and in fact, that's what the proofs of Little's theorem do. They keep on coming up with neater and neater ways to do that. Yes?
So why are these two equals?
Why are they equal? Okay, the question is, why are these two equal? The answer is, intuitively, I'm looking at this as being a reservoir. And time is coming in and building up, and time is going out. Now, if the values here exist, then they must balance, because I can't have time building up more than is being used up over the long run. So this represents, over time t, the amount of lifetime total that's brought into the system. And this represents, over time t, the amount of lifetime that's used up. And those things must balance in the long run. So we let t go to infinity, claim we can cancel the t out. Of course, that's a heuristic engineers or physicists argument. And then when you do that, you're left with the result. Now, the beauty of this, remember, is that the definition of system and the particular stochastic processes involved, well, this is very flexible, and stochastic processes involved is irrelevant. So this is a very powerful and general rule. Now, I want to apply this to some special cases. In particular, I'd like to apply it to the Erlang delay model right over here. So right here, for example, we have the average waiting time. We have a formula for average waiting time. So now I'm going to apply Little's formula to get a formula for the average number in Q. Let me erase this here. So let me call this average Q length. All right, now, to apply Little's formula, I want the Q to be the system. So here are my arrivals, and then here's my Q, and then here are my servers. So I'm going to take the system to be the Q. Now, what is the rate at which the customers enter the queue? And the answer is, well, if we have stability, then everybody who arrives enters here. Now, he may spend 0 time here, because if when he arrives there are servers available and nobody's waiting, then he will pass through this in 0 time. But that's okay. That's included in the average. So the arrival rate to the system is the same as the entry rate to the queue. The average number waiting in the queue, by definition, is expected queue length. So therefore, if L equals lambda W, this thing, that's the average number in the system or in the queue, is equal to lambda times the average time they spend in the queue. But how long do they spend in the queue? Well, by definition, that's the average waiting time. Now, typically, what you do is you calculate this, and you divide by lambda to get this. But in our case, we already have the average waiting time. So all I have to do is multiply through by lambda to get the average queue length. Okay, so if I multiply through by lambda, then I have here C of S and A. And now I have lambda times tau divided by S. But of course, lambda times tau divided by S is rho. So that becomes C of SA rho over 1 minus rho. So that's your average queue length. This is equation, let's see, average queue length, 4.27 in the textbook. No, wait a minute. This is, well, it's 3.37. I'm not actually, I don't believe it's in my textbook, but it's 3.37 in Bertzekis and Gallagher. In my case, I wasn't really interested in the average number in the queue. I'm interested in the average time you spend in the queue. But Bertzekis and Gallagher, on the other hand, what they did is their strategy was to calculate this first directly from the state probabilities and then divide by lambda to get the average waiting time. So their average waiting time formula is, let's see, I'm not sure where it is. I don't think, in fact, that they have a number for it. Okay, so this is an important result. It's the Erlang C value divided by rho over 1 minus rho. Now notice that that in the calculation of the expected queue length, we needed only the state probabilities for the Erlang delay model. And as you remember, in fact, when we derived those probabilities, I noted explicitly that those probabilities, that analysis, did not make any assumption about the order in which the customers are served. So if this statement is true, and this is independent of the order in which they're served, then this must be independent of the order in which they're served. So that proves that this formula is valid not only for FIFO, even though we derived it for FIFO, but in fact it's true for any order of service. Okay, so that makes this even, that makes the Little's formula more useful because it makes that proof easy, and it shows that this formula here is very, very robust. Okay, let me write down some other things that come out of Little's theorem. Okay, first of all, suppose that we had the Erlang B system. Okay, suppose that we're looking at Erlang B. So here's an example, the Erlang loss model. Okay, now, we have a formula for the carried load. But the carried load is the average number of busy servers. So A prime, the carried load, is in fact L in Little's formula. Now, according to Little's formula, the average number in the system, which is the carried load if the system is an Erlang-B system, is the rate at which they enter times the average time they spend. What is the rate at which the customers actually enter the Erlang-B system? Well, they arrive at rate lambda, and a fraction of them enter, and a fraction of them are turned away because they're blocked. The fraction that's blocked is given by the Erlang-B formula, and the fraction that enters, therefore, is 1 minus that. So this part right here, that in fact is what we've called lambda prime. It's the entry rate, which is the arrival rate times the fraction that enter. Now, when they enter, how much time do they spend in the system? Well, they spend their service time, because remember, they're entering right into the servers. The average service time is by definition tau. So this part right here, that's W. That's L. That's lambda prime. Lambda times tau by definition is A. So A prime, therefore, is equal to A times 1 minus the Erlang-B. Of course, we already knew that, but we obtained it by actually calculating the definition of average and doing some arithmetic. And now we don't need to do any arithmetic. We can see that this is actually a consequence of Little's formula. And we interpreted this. Actually, our interpretation was analogous to where this came from. Because what we said is the carried load is equal to the offered load multiplied by the fraction of the offered load that is in fact carried. So that was a verbal interpretation of this. Now, from this we got the idea that, well, suppose that S is infinity. If S is equal to infinity, then the fraction that is lost is 0, and therefore the carried load would be equal to the offered load. And that makes perfect sense, because if there's no losses, then everybody who arrives gets carried, and that again justifies the use of this terminology of offered load and carried load. So you can see that lots of things that have expected values in their definition are consequences of or related to Little's theorem. Okay, let's look back at some other applications of Little's theorem to the Erlang delay model. So first of all, what we have is we were able, using Little's theorem, to go from the average waiting time to the average queue length. Did I make a mistake here? Wait a minute. Let's see. This is the average queue length. So this is, okay, let me think about this for a moment. L equals lambda W. So average queue length is equal to lambda times E of W, and that's this right here. So this is the average queue length as given by this formula. Okay, so this is the other important formula right here. Nobody corrected me on that. So I guess I could write down any garbage, whatever, and get away with it. If you see a mistake, don't be shy about correcting me, because you're doing me a favor, right? Because this is being recorded for all posterity. So I really look like a jerk if I write down the wrong thing. Okay, another thing that we had was we said for the MMS, we said that the carried load was equal to the offered load. And the justification for that was, well, first of all, we calculated it by calculating the average number of busy servers. Or at least I said if you made that calculation, did the arithmetic, which is done in the solutions manual, then this is what it would reduce to. But now how can we, then we made the interpretive argument that, well, in an Erlang delay model, everything that arrives, every customer who arrives ultimately gets carried, and therefore the carried load should be the same as the offered load. But from Little's theorem, it follows also. Because from Little's theorem, it says that, well, the carried load, let's look at the carried load as the average number of busy servers. Okay, so here is our system now. Customers arrive, queue up, and then they enter the system. But now my system is right here. It's not the queue, it's the servers. So that's my system. So the rate at which they enter the system is the same rate at which they arrive. Because in the Erlang delay model, everybody who arrives enters, although they may be delayed by having to wait in the queue. So the entry rate, so here we have L, that's the A prime, equals lambda, the entry rate, lambda prime, which is the actual arrival rate, times the average service time, the average time they spend in the system. Since the system is the servers, that's the average service time, what we've called E of x. Well, I'll just write it as W here. In other words, L equals lambda W. The lambda is the arrival rate, and the W is the average service time, and the average number in service is the carried load. So the carried load is equal to arrival rate times average service time, which by definition is what we called offered load. Now this shows that in a system in which, like an Erlang delay model, the carried load equals the offered load, that is the arrival rate times average service time, is valid whether I have exponential service times or Poisson input. It doesn't make any difference. It's always true that the arrival rate times the average service time, if everybody who arrives enters, is going to be equal to the average number of busy servers. Okay, we had a formula for the average queue length. I'll write it down again. The average queue length, which was equal to the arrival rate times the average waiting time, and that's what we derived, that's equal to rho over 1 minus rho times the Erlang C value. And that's what I wrote over here. What's the average number in system? I'll call that N. That's the average, that's the total number in the system. Well, that would be the average number in the queue plus the average number in service. But the average number in service, by definition, that's the carried load, which of course is the same thing as the offered load. So that's going to give us this formula. Rho over 1 minus rho, Erlang C value, plus A. What's the average response time? By definition, the response time, or sometimes called sojourn time. Okay, so I'll call this response time or sojourn time. By definition, that's the average time it takes a customer from when he arrives until he leaves. So it's a sum of his waiting time plus his service time. So that would be the expected value of W plus his average service time tau. And that turns out to be equal to, therefore, C of SA divided by 1 minus rho S, that's the average waiting time, times tau, plus tau. Okay, so now we have various different performance formulas. We've got the average number of busy servers, which is the carried load, which is also equal to the offered load. And by the way, that means that rho, by definition, the carried load divided by the number of servers is the offered load divided by the number of servers. No matter whether I have Poisson input or some other input, no matter whether I have exponential service times or some other service time, and no matter whether the service is in order of arrival, reverse order of arrival, or anything else. So this is a very general, robust formula. Then I have a formula for the average number in the queue, it's given by that. The average number in the system is given by that. The average time it takes to flow through the system is given by that. And of course, the average waiting time itself, which I didn't write down again, but which is given by this right here. The average waiting time, of course, is that term right there. Now, it's interesting to look at these formulas for MM1. So I'll write here MM1. The reason is that MM1 is sort of like the standard thing that's given in the textbooks. In fact, in many textbooks, the authors treat MM1 first, separately, and then they treat the multi-server case. And in fact, that's what Persekis and Gallagher do. But of course, that's really inefficient because the one-server case is just a special case of the multi-server case. But for some reason, I guess because it's so much simpler to originally write the equations, that they often look at the MM1 by itself. Also, in terms of applications, at least in data networks, MM1 is probably more important than MMS. Now, for MM1, I can get those results now by just specializing these results by setting S equal to 1. So first of all, let's look at the formula for E of Q. Okay, for MM1, it turns out, as you know, that, well, let's see, what do we know for MM1? We know that the Erlang C of 1A is equal to A. Just plug into the formula, and that's the way it turns out. Running low on ink here. It also happens that for the MM1, the state probabilities happen to be simplified to the geometric, which is that Pj is equal to 1 minus rho, rho to the j. Okay, this is just an observation. This is a little bit more important. Remember that in the case of one server, the offered load will, in this case, the offered load is always equal to the carried load. The utilization is the carried load per server. In one server, therefore, the offered load is the same thing as the utilization, which is a nice thing to know. So that means if I go back over here to the formula for the expected queue length, when S is equal to 1, I can replace the Erlang C value by rho, and that's going to mean that the expected queue length has the formula rho squared over 1 minus rho. Notice, just like the average waiting time, that the expected queue length has the fact in it, has the 1 minus rho factor in the denominator, which means that as rho approaches 1, the average queue length goes to infinity, just what, of course, you already knew or expected. Of course, also, again, that this result and this result is independent of the order of service. It doesn't require FIFO service. Okay, the average waiting time, I'll write it here. For MM1, the formula is rho over 1 minus rho times tau. That comes out of here by setting the Erlang C value equal to rho and S equal to 1. Okay, so these are very simple formulas. And notice that the average waiting time measured in units of average service time is simply rho over 1 minus rho, which looks very much like the average queue length, which is rho squared over 1 minus rho, which tends to cause some confusion among students because they look at these formulas and different books tend to define things slightly differently or use slightly different notation, and they find out that everything looks like it has a rho or 1 minus rho or a rho squared in it, and they can't tell one formula from another. And it all seems rather arbitrary. Of course, it's not arbitrary. That's the way the formulas come out. Okay, what about the average number in system? That's from this formula right here. If I replace the Erlang C by rho and replace A by rho and simplify things, so I get this. I would have rho squared divided by 1 minus rho, that's this piece, plus rho. And then when I simplify this by putting this over a common denominator, 1 minus rho, it turns out that the answer is exactly rho over 1 minus rho. So again, you have sort of a confusion here. The average number in the system is almost like the average queue length and is the same as the average waiting time scaled in units of average service time, because the formulas are the same. The average response time, or sojourn time, now comes out of this formula with the average waiting time replaced by that guy right over there. And so it turns out that that's equal to 1 minus rho over tau, or times tau. So again, these formulas, which now all come easily out of Little's theorem, these formulas all hold for any order of service, and they're sometimes confusing in that they all look very similar because they all have a 1 minus rho in the denominator, and the numerator they've got a 1 or a rho squared. And so it's sometimes confusing to people, but that's the way it is. Now there are other applications of this, a little bit more sophisticated, and we'll get to those later, but that's not my point. My point now was to get in one place all these nice results for the standard queuing model, and notice the simplification that occurs when you let S be one server. Okay, so I think now we're probably ready to start looking at homework 3. So I don't think I've forgotten anything. Did I forget anything? Any questions about anything here? Yeah.
You write there
Response. This word is response.
below that.
And below that is sojourn. Yeah, this is the total time it takes from arrival to departure. So one terminology has it, well, the sojourn, that's like a length of a walk. So the total time for, see, some people confuse, or they define things differently, and they talk about the waiting time as the total time it takes to flow through the system. Some people call that system time. So I want to be, so my convention is to call the waiting time what you wait in the queue for service to begin, and then the time it takes to flow through the system, I call that sojourn time or response time. The reason it's sometimes called response time is that in computer science, if the server is a computer, from the viewpoint of the customer, he doesn't care how long he waits. He cares only how long it takes to get the answer. So if you're talking about, say, a telephone system, then the length of time you wait, that's bad, but the length of time you're being served, that's good. Maybe let's make it a restaurant. The length of time you wait, that's bad. The length of time you're getting served, that's good. You're having fun. So you wouldn't want to say that if you have a long sojourn time, that that's bad, because maybe that time is spent eating. But if your time is spent waiting, that's bad. So I want to separate the waiting time from the service time. Now, in the restaurant model, it's the waiting time that's a measure of performance, not the sojourn time or response time, because the system could be giving very good performance, very good response, but or I should say, yeah, it could be giving good response, but you could be spending a lot of time in the system, but that's good because that time is fun. On the other hand, in a computer system, if you're a job waiting for a CPU, you don't care how much time you spend before the CPU starts working on you. What you care about is how much time from when you make your request for service until your service is completed. And how much of that time, how it's divided up between waiting and service is irrelevant. So that's sometimes called the response time. That's the time it takes for the system to respond to you and send back its answer. So I use these two terms now interchangeably, response time and sojourn time. But be aware, some people call it system time, and some people call it waiting time. Some people get confuse or get confabulate or something like that. Waiting time and time spent in system. Okay, so let's look at homework 3, which I asked you to download. And it says, augment your code of homework 1, which is block customers cleared, so that it will now describe the case where the blocked customers wait in an infinite capacity queue and are served in FIFO order. Include code and output. And by the way, it should also include theoretical calculations. So this is something I'm going to add. In all problems, all the problems from now on, in fact, all so far, have concerned themselves with some calculations and some simulation. Now, for the simulation, I want to see a printout of the actual code you used, and I want to see the actual output that the code gave you, and then that's what you copy in the tables. For the theory, I didn't say it in the past because there was only a way to get the theory, which was to do it. And of course, you're always supposed to show your theory, explain how you got your answers, and then put those things in a table. But now, for these kind of standard models, there's another way to get the theory answer, and that is to just use the internet wisely, because these things are out there. So you can go to some canned software, some calculators, and specify to the calculator what model you have, and press the button, and it'll come back with the answer. So it's good to know that. Of course, different websites have different conventions for what they call things. So if you're going to use it, you have to be careful to identify things properly. But it's okay to use it because, in fact, in real life, that's often what people would do. It's already done for you. All the calculations are done, and they're probably correct. So from my point of view, if you can go out on the internet and find a calculator that calculates your model, that's okay. You can use that as a check. But I also want you to do the calculations yourself and show what the calculations are. So I'm taking the viewpoint now that the stuff is out there. It's okay to look at it. It's a check to see whether or not you did it right. But if it differs from your calculation, that might not be because your calculation is wrong. It might be because you're misinterpreting the symbols that are given in the on the website. So anyhow, if you use a calculation, an external model you get from someplace else, write down what that is, write down what answers you got, and write down the answers that you got through your calculation, and show how you got it. Because after all, in the end, if all you do is look things up, then there's really no point to this. So you're trying to see whether you understand these things or not. Okay, so let's go back to homework 3. It says, fill in the table. Cases 1 through 4 use the same assumptions as homework 1 about the input process and the service times. In each theory box, write the theoretical value if you can calculate it. If not, write NA, which means not applicable. In case 1, show all formulas used. In every other case, if you give a theory answer, explain how you arrived at that answer. Run each simulation for at least 100,000 arrivals, 1 million if feasible. Of course, if you can't do 100,000 for some reason, you have an old computer, can't count high or something like that, do as many as you can. But the longer the run, the more accurate, more likely it is, the closer the theory is going to be to the simulation. And if everything works out right, it should be very close. Take the unit of measurement to be the average service time, 2.4 seconds, and take the number of servers to be 10. Now, where it says the unit of measurement to be the average service time, this is different. This is convention, but it's different from what we did before. So before, like in homework 1, we talked about an arrival rate and a service time. I think the service time was something like 2.4 seconds. So now you're going to take 2.4 seconds as being the unit of time, so that one time unit is 2.4 seconds. 2 time units are 4.8 seconds, and so forth. So the convention is that you always take the average service time as being the unit of measurement, and then you don't have to say whether you're talking about seconds or hours or minutes or anything like that. Everything is measured in service times. And people sometimes have a confusion about about scaling the time in 1 units versus these general units, and so it's worth knowing. So I originally stated the problem in terms of seconds, but now I want you to convert to average service times as the unit of measurement. But first, before I do that, I think I should probably talk about the strategy for the simulation, because I think once you know the formulas, which you know now, the formulas are easy. The only thing I'm asking you to do that's different from before in terms of formulas is when I asked you to calculate Erlang B, most people just calculated it by just writing out the formula and calculating all the terms. Now I'm saying that's pretty unsophisticated. The way to calculate the Erlang C is to use the formula that I gave you that relates Erlang C to Erlang B and calculate the Erlang B iteratively. That's the fastest. It should be done in a program. You don't want to do this by hand. For some reason, computer science students, unless you tell them, never use a computer as a calculator. They just don't think that way. But after all, that's what computers were originally invented for. They're just really big calculators. So you should make your calculations, write a little program to make the calculations, and it's faster, it's much more accurate, and also it would be applicable if you had zillions of servers, which of course you could never do by hand. Of course, in this case you have only 10, but that's what I'm asking you to do. But the theory part seems to me to be easy, although I'll discuss it next time if we have time, or we will have time. What I want to do now is discuss the simulation, which I think is the more interesting part, actually. Okay, so any questions about the stuff I'm erasing? Speak now or forever hold your peace, at least on this topic. All right, so you're supposed to take homework 1 and upgrade it. First of all, let me recognize or mention what I have here is, this is the original statement for homework 1, and you could see that I just added a couple of statements here, and that was enough. I'm write it by hand on 1 page in BASIC, and I can still handle the new problem. So that's a hint. This shouldn't take much in the way of code. Now, you'll notice that in homework 1, I asked you to calculate the fraction of customers who were blocked and the fraction of time you were in the blocking state. And if you have Poisson input, those two things turn out to be equal. That's pasta. And I was trying to illustrate that, so I asked you in the simulation to calculate both and show that you got the same numbers when you had Poisson input and different numbers when you did not have Poisson input. But I think now this is beating a dead horse, so I don't have to do this every time. So from now on, I don't want to calculate the fraction of time I'm in the blocking state. I just want to calculate the fraction of customers who find that. So I'll eliminate that part of the simulation. So in our simulation, in the code that I gave you, there was statement 220 through 260. And now I'm saying, okay, get rid of that. Just get those out of the code. We're not going to worry about those anymore. And then you take the rest of the code that I gave you and update it, upgrade it so it handles the queue, and that's what I'm going to show you how to do now. Except I'm not going to give you the code, I'm going to give you the reasoning behind it. So here's our model. Let's say this is our timeline, and here is, let's say, server number 1, server number 2, server number 3. Let's say we have 3 servers for the sake of this diagram. So what I do is I generate an inter-arrival time. That is, I have 2 earns here. There's the inter-arrival time earn, and there's the service time earn. I reach the inter-arrival time earn. I generate an inter-arrival time. Then I look for a server. So I have an array in which for each server I have the time at which it's next going to become available for service. And I check my current time. This is now my current time. I check server number 1 against the current time. If the server is available, then I can carry the call on that server. And if it's not available, then I go to the next one, and so on. So I look at server number 1. In this case, let's say he's idle. So then I reach into the service time earn, and I make him busy. And then I update the state of that server. Then I generate arrival number 2. Let's say he occurs here. And of course, I've moved my clock from there to here by adding the inter-arrival time to the old arrival time. Then I look at server number 1. He's busy. Server number 2 is available. So I sample from the service time earn, and I make the server busy for that length of time. And I do it again. Let's say he comes here. This guy would be carried on server number 1. Then again, this guy would be carried on server number 3. Then again, this guy would be blocked on server number 1, blocked on server number 2, blocked on server number 3. So in homework 1, he's an overflow call. So I count him, and at the end, I divide the number of overflows by the number of arrivals, and that gives me the fraction of calls that were lost due to blocking. Okay. Now, this guy is not going to be thrown away. Now he's going to be put on the queue, and he's going to be served later. So here's the way I want to handle that. Let's say that this goes, let me extend these a little bit so it makes the picture clearer. This guy's going to be on the queue. If I have FIFO service, what that means is that he's going to be handled by the next server that's going to become available. So what I do is I look through the servers, and I find the server that is next available for service. In other words, I find the minimum of this value, and that value. In this diagram, it's this one right here. So I can do that in about 3 or 4 instructions in BASIC. Okay, so I find the minimum. I know this guy is going to be carried on that server. Okay, first of all, how long is he going to wait? Well, his waiting time is the difference between the time at which the server becomes available and the time at which he arrived. So at that moment, I can calculate that guy's waiting time. Now, when he's served, he's going to have a service time. So I reach into the service time earn, and I pull out a service time, and I make this server busy for that additional length of time. That's his service time. Then I update the state of the server so that the time at which he is next available for service is that time plus the new service time, and then I generate the next customer. Okay? Let's say the next customer arrives here. Well, he's going to be blocked there. He's going to be blocked there. He's going to be blocked there. So it would have been an overflow call, but now he goes on the queue. But notice that I don't have any separate structure for the queue. That's what makes this so easy. Because I say, okay, this guy is going to be carried on the server that's going to be next available for service. Well, from this diagram, you can look that when I find the minimum of that, and that, it's this one right here. So therefore, he's going to be carried on server 3. His waiting time is going to be that value right there. The difference between when that server would have become available and the current time. And then I reach into the service time earn, and I draw his service time, and I add it to this. And then I update the state of server number 3, and I generate the next arrival. And the next arrival will be carried by this server after waiting that long. I generate his service time, update the state of the server, generate the next arrival. The next arrival sees server number 2 available. His waiting time is 0, and I handle him just as if there were no queue, just as before. So I've never had to put up a separate structure for the queue. All I do is recognize that whenever a customer is blocked, then I look at the time at which the next available server will become available. And I know that the difference between that time and the current time is the waiting time for this blocked customer. And then I go to the server that's going to carry them eventually. I make the server busy for an additional time, which is the service time of that new customer, and then I continue on. And I just keep records as I go along. So I have the waiting times of all the customers, which means that later I can calculate the average waiting time, and I can calculate the fraction of waiting times less than or equal to or greater than any t, if that's what I want to calculate. Is there a question back there?
No, not anymore.
Okay. The answer to that question was no, there's no question. All right, so this simulation is simple. So when you remove the instructions that you had before that calculate the fraction of time you're in the blocking state, and you replace them with the instruction to calculate the waiting times, your program is about the same length as before. Okay? Any questions about this? Yeah.
For those of us who realize that C frankly sucks for what we're doing here,
Right.
well, I know you mentioned it earlier, what would be the best way to get a basic program to run through, compile, and stuff like that?
Okay. The question was something about C sucks or something like that. So how do you get basic? If you send me an email saying send basic, I'll send back some stuff that I collected from students who told me where they got it. And I think that there's various versions of basic. I think the standard QBasic is very slow, although it's simple. I think Visual Basic is faster, but maybe more complicated. And there's something called UBasic. So anybody who's good with computer science should be able to find these things. So UBasic, I think, is the most sophisticated version of BASIC. So it's probably the fastest and also has the most capability, but it might also be more complicated, more overhead. I don't know. Okay, so let's go through start looking at what's required for this homework problem. I'll do that over here. These homework problems tend to build on each other, so that it's important to get these theory right and to get the simulation right, because if you do that, each successive homework is not too big a jump from the previous one. But if you start at the end, then it's probably pretty difficult. Okay, so it says fill in the table. So let's see what the table says. Looks like this. There's going to be two cases. There's going to be lambda is equal to 4.2 arrivals per unit time. Now, actually, it was given, I think, originally as the units, I think, were seconds. So it was 4.2 arrivals per second. But now remember that we're changing the units. So this is in seconds, but I'm asking you to measure the things in the table in units of average service time. So that means that when you run the simulation, you can either run it as it's already written in seconds, and then take the answers at the end and change the units so that now it's in service times, or you can do it originally in the simulation program so that it calculates everything originally in terms of service times. I think the easiest way to do it is to do it the old way and then take everything and divide or multiply, as the case may be, by 2.4 to go from seconds to service times. Okay, so I want to look at two cases. One is lambda is equal to 4, and the other is lambda is equal to 4.2. The reason for that is that when lambda is equal to 4, the number of Erlangs is 9.6. And we have 10 servers, and so we have convergence. But when lambda is equal to 4.2, the number of Erlangs is more than 10, and so you don't have convergence. Now, the theory predicts, for the case where there's no convergence, it's going to predict that the queue lengths are infinite, that the average waiting time is infinite, and so on. But in the simulation, of course, nothing is infinite. All that happens is that in the case in which you have convergence, the longer you run the simulation, the more tightly it converges to the theoretical values. Whereas in the case where you don't have convergence, the longer you run the simulation, the bigger the queue length gets and the bigger the average waiting time gets. and it would approach infinity if you ran the simulation in infinite length of time. So it's interesting to compare those two cases, because in terms of numbers, 4 and 4.2 doesn't look like it's that different. But in terms of the results, they're extremely different. Okay, then it's going to ask you to calculate some stuff. One is rho, one is the average waiting time, and then the others, now this you have to get this in your simulation. The probability of waiting time greater than 0, probability of waiting time greater than 1, and so forth. The way you interpret that is this is the average waiting time in units of average service time. This is the fraction of who wait greater than 0. In other words, it's going to be given at first by the Erlang C value, probability of having to wait. This is the probability of waiting more than 1 service time, not more than 1 second. So if this is measured in units of average service time, this is measured in units of average service time. So waiting more than 1 service time is the same as waiting more than 2.4 seconds. So you have to take that into account, have the right values when you write your simulation. And also, as the simulation was written in homework 1, you didn't have these values here because there was no waiting. So you have to put them in the code. You have to say something like, if W is greater than 1, then count it. If W is greater than 2, then count it. And at the end, you divide the number who waited greater than 1 by the total number generated. That gives you the fraction who wait greater than 1. And then over here, the number that waited greater than 2 divided by the number generated, that's the fraction who wait greater than 2. And of course, these values should agree with the theoretical formula that we just derived, that I erased. Okay, then there are the 4 cases. So here's case number 1, and it asks you to calculate theory and simulation. Now, case number 1, that's the case where everything agrees with our theory, because this is by definition Poisson input exponential service times. So first of all, what's the utilization going to be? And the answer is, well, it's going to be 96%, because we know that we're generating 9.6 Erlangs. There are 10 servers. Everybody who arrives gets served, so the utilization will be 96%. Now, in a simulation, what you do is I gave you some code. I told you already how to calculate carried load. So you calculate the carried load, which you're supposed to convince yourself is the same as adding up all of the service times for all of the customers that are carried, and then dividing that by the total time over which you have simulated. And that'll give you the carried load in Erlangs. Then you divide by 10, because there are 10 servers. That'll give you the utilization, and that should turn out to be very close to 96%. Then there's case number 2, and 3, and 4. Okay, case number 2, got the same stuff. In every case, it's the same stuff, theory and simulation. Case number 2, the assumption is that you have Poisson input but constant service times. So now, some of the theory is going to be the same as before and some is not. Because if you require exponential service times, then the theory is not going to carry over. And if you don't require exponential service times, then it will. So for example, I said from Little's formula that the formula for the utilization, if everybody arrives as carried, is going to be exactly the same as before. So in fact, in every case, the theory is going to be 96% for the utilization. So when you run the simulation, you'll see that that's true. So that'll show you the robustness of the simulation of the utilization measure. And it also shows you that it doesn't really give you that much information, because as you'll see, the probabilities and the average waiting times, they can be wildly different from case to case, but they're all going to have the same utilization. So measuring the utilization by itself doesn't tell you that much. Well, it looks like we're running out of time, so I'll start here next time and give you some hints as to what goes on when you fill in these columns. But mostly, you should be able to figure it out yourself. So think about it and have your questions ready next time. Any questions now? Everybody up to date? Okay, see you all on Wednesday.